One of the main ideas in section 10.5 is the idea of when you add or subtract, you generally have to add or subtract like terms. So you guys know that 3x plus 4x equals 7x, and you may even be aware of why it does, and the answer to why it does is that you can rewrite this using the distributive property this way, and then 3 plus 4 is 7, and you have 7x. But something to realize here is that this is true no matter what x is. So specifically, if x is the square root of 5, this means that 3 square roots of 5 plus 4 square roots of 5 is 7 square roots of 5. Just the same as x's. Now if you had 3x plus 4y, that would be trouble because you can't add things that are not alike, and so here you would just be stuck. So if you have 3 times the square root of 5 plus 4 times the square root of 7, you are just stuck. There's nothing you can do. This is done. However, if you have 3 times the square root of 5 plus I don't know, 2 times the square root of 45, your first instinct is that the square root of 5 and the square root of 45 are different, and so there's nothing you can do. But the question is, do these ideas of simplifying that we've been studying in chapter 10, do they help? So let's try. How is 45 built? It's built out of 9 times 5, 3 times 3 times 5. So this problem can be rewritten. Instead of the square root of 45, it can be the square root of 3 times the square root of 3 times the square root of 5. Do you see what's going to happen? Can you see it coming? These two pair off and give us just a plain 3, and there's a leftover square root of 5. And so this is 3 times the square root of 5 plus 6 times the square root of 5. 3 of them plus 6 of them is 9 of those square roots of 5. So even though these looked different, they simplified into terms that had like square roots. And then we could actually make progress and add. That's a pretty nifty thing. So what do you do when you start to multiply these pieces? Well, this is a lot like x plus 3 times x minus 3. It's 2 terms times 2 terms. It's FOIL, and we get x squared, and we get minus 3x, and we get plus 3x, and we get minus 9, and we collect like terms, and so we have x squared minus 9. Well, what do we do here? We do 3 times 3, which of course will be 9, but I'll just do it later. Minus 3 times the square root of 7 plus 3 times the square root of 7 minus square root of 7 times the square root of 7. And now we analyze parts. This is 9. This is minus 3 of these plus 3 of the same thing. Negative 3x plus 3x, or negative 3 of something plus 3 of the same thing. That's just nothing. And over here, these pair off to a regular 7. So we have 9 take away 7. The multiplication of these two weird things is just exactly 2. Very strange, but not too hard. Similarly, on this problem, don't distribute the 2 across a plus sign or a minus sign. Don't do that. Instead, write down what this means. It means 2 of these multiplied together. That's what this 2, this power of 2 means. And so we have 4, and we have plus 2 square roots of 3, plus 2 more square roots of 3, plus the square root of 3 times the square root of 3. Let's analyze parts. 2 of these plus 2 more of these is 4 of those square roots of 3. Square root of 3 times itself, that's exactly 3. 4 plus 3 is 7, and we have a final answer of 7 plus 4 square roots of 3. Pretty nifty. So this problem gets pretty tough. We're trying to rationalize the denominator. We're trying to make the denominator root-free. And that is a pretty tough problem because we have to know enough to know what you could multiply the bottom by that would make it root-free, and most things don't work, and there's lots of things that are reasonable, good tries that smart people try, and it fails. If it was a Math 29 class, I'd show you all the things that fail, but instead I'm going to just show you the thing that works. It's called a conjugate, and the conjugate of this denominator is almost exactly the same. It has a 2, and it has a square root of 3. But to do its job of getting rid of roots, the conjugate has to have the opposite sign. So since this is a minus, it has a plus. And what you do to the bottom because you need to, you do to the top because you have to follow what you did on the bottom. Now we're multiplying this fraction by 1, so we're only changing the way it looks. But notice what happens in the denominator when we do our FOIL. 2 times 2 is 4. Here we're getting 2 square roots of 3. Here we're getting minus 2 square roots of 3. Those are gone. And we have a negative times a positive, which is a negative. Square root of 3 times square root of 3. Do you see that the denominator is going to be root-free? Now in the numerator you can get just a bunch of ugly junk. 2 times 2 is 4. Plus 2 square roots of 3. Plus 2 square roots of 7. Plus the square root of 7 times the square root of 3. So looking at the parts in the numerator, we have a 4, and we have plus 2 square roots of 3, and we have plus 2 times the square root of 7. Plus, and these two parts are leftovers, both of them, so we put them in one leftover container. This is 3, so we have 4 take away 3, which is 1. And generally we don't put 1 on the bottom by itself. It's unnecessary. So in this particular problem, this divided by this equals this, which is very strange. But it all has to do with conjugates. And you'll note that this is the kind of thing that will be on an exam. You'll see a problem like this on the exam. So when you do problem 63 and you look at this example, and maybe you look at a few more examples in the book, don't be confused. There will be something like this on the exam. That's sort of a promise.